Welcome, curious minds, to the deep dive. Today we're setting off on, well, an incredible journey. Strange new worlds. The search for alien planets and life beyond our solar system.
Sounds exciting.
It really is. I mean, imagine just a couple of decades ago, our solar system was pretty much the only planetary system we knew for sure.
That's right.
Now, we know of hundreds, thousands more waiting to be confirmed. We are truly living in an extraordinary age of cosmic discovery.
It's a breathtaking transformation, really.
Right.
And the fundamental question driving astronomers today is, well, it's profoundly simple, but also immensely complex.
Which is?
Is our solar system, with its warm, wet, rocky Earth teeming with life, is that the exception, or is it the norm out there?
A cosmic coin toss, sort of.
Exactly. And humanity's wrestled with this idea for, well, millennia.
And it really isn't a new question at all, is it? I was genuinely surprised actually digging into this to find a Chinese scholar from the Song Dynasty, Tang Mu, writing between 960 and 1279, and he put it so perfectly, he said, how unreasonable it would be to suppose that, besides the Earth and the sky that we can see, there are no other skies and no other Earths.
That's fantastic. An ancient intuition, really, echoing in modern science. It's truly remarkable how, even with those early philosophical insights, the actual scientific tools to answer these questions were centuries away.
Yeah.
We're still, in a way, kind of the Bronze Age of planet hunting.
Right. Still early days.
But the discoveries we're making already, they're challenging our deepest preconceptions and bringing us right to the edge of some potentially monumental revelations about our place in the cosmos.
Okay, so let's unpack this cosmic detective story. Maybe start with the long gaze humanity's historical quest for other worlds. It's quite a journey from just philosophy to, well, actual verifiable facts.
Absolutely. For centuries, the dominant view, championed by ancient Greek philosophers like Plato and Aristotle, was that Earth was unique, special, the center of everything.
A geocentric model.
Exactly. But these dissenting voices, like Tang Mu we mentioned, they slowly began to chip away at this idea of singularity.
And then came the telescope. That wasn't just expanding our vision, it completely revolutionized our understanding, didn't it?
Oh, massively. Nicholas Copernicus's sun-centered model, proposed way back in 1543, laid the theoretical groundwork.
Right.
But it was Galileo's observations in 1610, his actual looking through the telescope, that provided the undeniable visual proof.
What did he see?
He saw Jupiter's moons orbiting Jupiter, not Earth. He saw Venus going through phases, just like Copernicus predicted. And maybe most dramatically, his sketches of the moon.
Ah, yeah, the mountains and valleys.
Exactly. They showed mountains and valleys. Suddenly, the moon wasn't just a perfect celestial orb. It was another world with familiar topography.
Yeah.
It just shattered that old geocentric bias.
Incredible.
And even as these telescopic observations were redefining our cosmic neighborhood, some early ideas about how planets actually form suggested they should be common.
Like who?
Well, in the 18th century, you had Immanuel Kant proposing that planets sort of coalesced from a diffuse cloud around the young sun.
Okay.
Then, about 40 years later, Pierre-Simon Laplace developed his solar nebula model. Both these ideas basically suggested that planets were a natural, almost inevitable result of star birth.
Which is good news for planet hunters today, right?
It is, because our modern understanding of planet formation actually resembles Kant's early ideas quite closely.
Yeah.
It suggests planets should be out there in large numbers.
It's still amazing, though, thinking back, that for so long, astronomy faced this almost insurmountable challenge, right? Studying these incredibly distant objects with just feeble light.
Absolutely. The French philosopher Auguste Comte even declared, I think it was 1835, that the chemical composition of stars was beyond our ken for eternity.
Wow. Talk about being wrong.
Completely wrong. But then this quiet revolution started with Joseph Fraunhofer. He meticulously recorded hundreds of dark lines in the solar spectrum.
Just faint black bars.
Yeah, faint black bars cutting across the rainbow of starlight. He died young, sadly. But his work eventually led to this profound realization. Those lines were like fingerprints. They reveal that stars are made of the same stuff as the world around us.
Bringing the stars closer?
Precisely. His epitaph, Approxima Vicidera, he brought the stars closer, captures it perfectly. He bridged that huge cosmic gap.
And it wasn't just about mapping stars anymore, was it? People like William and Margaret Lindsay Huggins took spectroscopy further.
Right. They use it to understand the physical nature, the chemical makeup of stars and nebulae. That was the true birth of modern astrophysics. It transformed astronomy from just charting positions into a quest to understand the universe's actual composition.
That shift in perspective is just
Yeah.
huge. When you think about Giordano Bruno,
Burned at the stake in 1600.
yeah, for believing stars were other suns with their own planets. And now, school children write essays about exoplanets.
It's an incredible turnaround, from heresy to homework, basically.
Mm.
A dramatic shift in how we see ourselves in the cosmos.
Okay, so from that historical view, let's dive into the cosmic kitchen. How do these planetary systems actually take shape? We can actually see these stellar nurseries, can't we?
Oh, yes. Take the Orion Nebula. It's one of the closest, about 1,500 light years away. It's this vibrant, chaotic cloud, just bustling with roughly 3,000 very young stars.
Really young. Like how young?
Barely a million years old, packed into just a few light years across. It's like watching a city being built, cosmically speaking.
Wow. So where do they come from?
Well, the story of stars and planets begins in these vast, cold, dusty, molecular clouds. William Herschel called them holes in the heavens.
Because they look like dark patches.
Exactly, dark patches against the starry background. These clouds, under their own immense gravity, they slowly collapse. As they collapse, they start to spin faster and faster.
Like a figure skater pulling their arms in.
Precisely. Eventually forming these dense, glowing protostars, and often these newborn stars shoot out powerful pairs of glowing jets.
Right, I've seen pictures of those, Herbig-Haro objects.
That's them, striking structures, perpendicular to the spinning disk around the protostar.
And those disks, that's the crucial part for planets, isn't it?
Absolutely. We see a telltale sign around maybe 50 to 90% of very young stars, something called an infrared excess.
Meaning extra heat.
Extra heat, exactly. It's heat radiating from a swirling disk of dust and gas surrounding the protostar. That's the cosmic construction zone. These protoplanetary disks, typically a few hundred astronomical units across.
So hundreds of times the Earth-Sun distance.
Right, huge. And they contain more than enough raw material, dust, and gas to make a planetary system like ours. They are, quite literally, planet factories in action.
Okay, so you have the factory, you have the raw materials, dust grains. How do tiny dust grains become, planets? That seems like a big leap.
It is. That's the core mystery, the sicking problem. How do they clump together? Experiments in microgravity done by Jürgen Bloom and his team.
On Vomit comets and the space shuttle.
Yeah, exactly. Those showed that dust grains don't just form neat spheres. They form these stringy structures, fluffy aggregates that can stick together better.
Interesting.
Other ideas involve things like aerodynamic capture or maybe turbulent gas motions, as Anders Johansson suggested, helping to directly form asteroid-sized objects called planetesimals. Think of it like pebbles suddenly forming in a swirling stream of gas.
Okay, so you get these planetesimals, these sort of proto-asteroids. Then what?
Then the process speeds up. Within a few million years, these cosmic pebbles collide, they stick together, they accrete, growing into moon-sized objects, and then eventually into rocky planets like Earth and Mars.
But what about the gas giants, like Jupiter?
That happens further out, beyond what we call the snow line.
Where it's cold enough for ice.
Right. Ice acts like a cosmic superglue out there. It adds a lot more solid material. This allows solid cores to grow much bigger, much faster, maybe up to 10 Earth masses.
Like rolling a snowball downhill.
Good analogy.
Yeah.
These massive cores then become gravitational vacuum cleaners, basically. They sweep up enormous amounts of hydrogen and helium gas from the disk to become giants like Jupiter or Saturn.
And that takes millions of years.
Typically, yeah. Though there's an alternative theory from Alan Boss suggesting some giant planets might form even faster through a direct, rapid collapse of parts of the disk itself. Less of a slow build, more of a sudden clumping.
Do we have actual pictures of this happening? Proof.
We have powerful snapshots. Back in the early 80s, the IRAS satellite, the infrared astronomy satellite, showed disks around young stars that seemed to be evolving. Some had inner holes cleared out.
Like something had swept through.
Exactly. A strong hint that planet formation was already underway. And more recently, Hubble. The Hubble Space Telescope has given us incredibly detailed images showing these disks shaping and changing over time. It confirms our models are, broadly speaking, on the right track.
Speaking of formation, our own moon. It's got a pretty wild origin story, doesn't it? The giant impact theory.
Oh yeah, truly dramatic. The prevailing idea is that a Mars-sized rogue planet slammed into a still warm young Earth, maybe 50 million years after the sun formed.
Wow, a planetary collision.
A huge one. And this catastrophic event explains a lot about the moon, why it has so little iron, why it's so dry. The debris mostly came from the rocky outer layers, the mantles, of both bodies. Any water or other volatiles would have just boiled away into space during that immense impact.
So the early solar system wasn't this neat, orderly place. It was chaotic.
More like a cosmic billiard table, absolutely.
Yeah.
And that kind of intense gravitational jostling wasn't a one-off event. There was also the mystery of the late heavy bombardment.
What was that?
It was an intense pelting of the inner solar system by asteroids and comets, happening around 3.9 billion years ago. This was long after the planets themselves had basically formed.
So why did it happen then?
Well, the thinking is it might have been due to gravitational interactions between the giant planets. Maybe Neptune migrated outward, stirring things up. Or maybe Jupiter and Saturn entered what we call resonant orbits.
Yeah. Meaning they lined up gravitationally.
Yeah, like a cosmic dance where their gravitational poles reinforced each other rhythmically. This could build up energy and fling smaller bodies, asteroids, and comets all over the place, including towards the inner planets. It paints a picture of a far more dynamic and frankly violent early solar system than we used to imagine.
Okay, so we know planets form, possibly quite often, and that solar systems can be chaotic. How do we actually find these exoplanets? Let's talk about indirect detection. For a long time, the main idea was looking for tiny wobbles in a star's position on the sky. Right. Astrometry.
That was the hope, yes. But it had a really frustrating history. There was a whole long controversial saga with Peter Van de Kamp and Barnard's star.
A science fiction favorite.
It was. But his claims of planets around it were eventually shown to be due to errors in his telescope, not actual planets. It kind of soured the mood scientifically for a while, made people very skeptical.
So astrometry didn't quite pan out initially. What worked?
The breakthrough came from looking for a different kind of stellar wobble. Not its position, but its speed towards and away from us. Gordon Walker and his colleagues, using these new, incredibly precise digital detectors, they applied the Doppler effect. They measured tiny shifts in the star's light color towards blue as it wobbled slightly towards us, towards red as it wobbled away.
Like the sound of a siren changing pitch.
Exactly like that. A tiny cosmic siren signaling an invisible planet was pulling on the star. This radial velocity method, that's what really opened the door.
And then 1995, the big one.
51 Pegasi b, game changer. Michel Mayor and Didier Queloz found the first planet around a normal, sun-like star.
But it was weird, wasn't it?
Oh, completely weird. It was a hot Jupiter, a gas giant like Jupiter, but whipping around its star in a scorching 4.2-day orbit. Queloz apparently thought it was a bug in their brand new instrument at first because it was just so unexpected.
Because Jupiter takes 12 years.
Exactly. This discovery just shattered the old idea that giant planets had to form way out in the cold, distant parts of a solar system like ours.
I bet there was skepticism.
Oh, intense skepticism initially. But then came rapid confirmations, other discoveries by teams like Jeffrey Marcy and Paul Butler. They quickly built up a whole census of these hot Jupiters, proving they were real, maybe even common. This didn't just find a planet. It revealed a whole new class of planetary system we hadn't imagined. It forced everyone to rethink how planets form and, crucially, how they might migrate inwards after forming.
And the discoveries just kept coming after that.
They really did. We quickly found systems with multiple planets like Upsilon Andromedae. Deborah Fisher found a third planet in that system, sort of an interloper that filled out the picture.
Right.
And even more unexpected were those pulsar planets Alexander Volzan found back in '92. Earth mass, moon mass planets orbiting a pulsar, the dead, spinning cinder of a massive star.
Wow. Planets forming even after a star dies.
It seems so. It showed planets could form or maybe reform, even in the most extreme environments.
Okay, so that's the wobble method. What about the dip method? Transits.
Right, transits. This technique actually has some cool historical echoes. Think back to the transits of Venus.
Kepler, Captain Cook in Tahiti.
Exactly. Those were used to measure the astronomical unit, the Earth-Sun distance, a fundamental measurement.
But for exoplanets, it's different.
For exoplanets, we're looking for tiny periodic dips in a star's brightness. If a planet's orbit is lined up just right, it passes directly in front of its star from our point of view, blocking a tiny fraction of the starlight.
Like a mini eclipse.
A very, very mini one. Tim Brown and David Charbonneau used a small telescope, STARE, to get the first confirmation of a transiting planet this way, HD 2009458b. And it turned out to be this weirdly bloated gas giant, much larger in size than its mass suggested it should be.
What's really cool about transits, though, is you can study atmospheres, right?
That's the really powerful part. When the planet passes in front of the star, some of the starlight filters through the planet's atmosphere on its way to us. By looking at which colors, which wavelengths of light get absorbed or blocked.
You can tell what the atmosphere is made of.
Exactly. We've detected sodium in HD 2Vol9458b's atmosphere this way. We've even seen hydrogen gas literally escaping from another hot Jupiter, WSP-12b. It's so close to its star, it's being tidally stretched into an egg shape, and its atmosphere is boiling off.
Wow. Creating weather reports for alien worlds.
Pretty much. Researchers like Heather Knudsen have even managed to map the heat distribution across an exoplanet, figuring out the temperature difference between its permanent day and night sides. It's incredible detail from so far away.
Okay, one more indirect method. Warped light, or microlensing. This sounds like science fiction.
It's straight out of Einstein's general relativity. Imagine you're looking at a distant star, and by chance another star passes exactly in front of it from our perspective.
Okay.
Einstein predicted that the gravity of the foreground star would act like a giant lens, bending and magnifying the light from the background star. Makes it temporarily look brighter.
Like a cosmic magnifying glass?
Precisely. Now here's the clever part. If that foreground star, the lens star, has a planet orbiting it, that planet's own gravity creates a second, much shorter, tinier distortion in that magnified light. A little extra blip.
And that blip tells you there's a planet.
That blip reveals the planet's presence and can even tell us something about its mass and orbit.
Amazing. And this involves amateur astronomers, too.
It does. It highlights the power of citizen science. Jenny McCormick, an amateur astronomer in New Zealand, she provided absolutely superb quality data from her backyard observatory that was crucial in confirming a planet found this way. OGLE 2005 BLG 071, about 5.5 times Earth's mass.
That's fantastic.
It really is. Microlensing is also really important for getting a handle on the overall demographics of planets across the galaxy. Because you can find planets further out from their stars and around different types of stars. It gives us a broader picture. And so far, it suggests that planets around the mass of Neptune might actually be the most common type out there.
Interesting. So not Earth's, not Jupiter's, but Neptune's as the most common.
Based on current microlensing results, yes, that seems to be the trend.
So as we find more and more of these strange new worlds, the lines between what we thought were distinct categories, stars, planets, they seem to be blurring a bit.
They really are. The discovery of brown dwarfs is a perfect example of this.
Okay, what exactly are brown dwarfs?
Think of them as Lilliputian bodies bridging the mass gap between the biggest planets, like Jupiter, and the smallest stars. They're roughly, say, 13 to 80 times the mass of Jupiter.
So too small to be stars, too big to be planets.
Pretty much. They're not massive enough to sustain the steady hydrogen fusion that powers stars, like our sun. However, the ones above about 13 Jupiter masses can briefly fuse deuterium, which is a heavier type of hydrogen. A little bit of fusion, but not sustained.
And they look like oil.
Well, when they're young, they glow dimly, resembling very faint stars.
Yeah.
But they don't have that internal furnace, so they just cool down over billions of years. As they cool, their atmospheres can actually develop clouds, maybe even rain made of things like molten iron. They become much more planet-esque over time.
Who figured these out?
Shiv Kumar theorized about these black dwarfs, as he called them, back in the 60s. Jill Tarter, who's famous for her work with SETI,
Right.
she coined the term brown dwarf. But the actual discoveries came much later, around 1995. Objects like PPL-15, Tide 1, and especially Gliese 299b that was considered the first definitive brown dwarf. They found methane in its atmosphere.
Which is a sign of a giant planet, not a star.
Exactly. That was a key piece of evidence.
How do they form? Are they failed stars or superplanets?
That's a big debate. One idea is sibling rivalry. Maybe they start forming like stars in a cluster but get gravitationally kicked out before they can gather enough mass.
Okay.
The other idea is turbulent collapse. Maybe they form directly from smaller, collapsing clumps within the big molecular cloud, kind of like stars, but just starting smaller.
Which way is the evidence leaning?
Well, observations show that many, maybe most, brown dwarfs have long-lived disks of dust and gas around them, just like young stars.
Disks where planets could form.
Potentially, yes. The fact that these disks are common and seem to last a long time suggests that most brown dwarfs probably form in situ, like small stars, rather than being ejected runts. And that's good news for the possibility of planet formation around them.
Which leads to this idea of a planemo. What's that?
It's a term, short for planetary mass object, used for these really low-mass brown dwarfs, maybe below the 13 Jupiter mass deuterium burning limit, and also for planets that might have been ejected and are now just wandering through space alone without a parent star. Free-floating planets.
Wow. Could those have planets orbiting them? Planets around planemos.
It's a wild but intriguing question. Could planets, maybe even Earth-sized ones, form the disks that we see around brown dwarfs, these objects that aren't much heavier than Jupiter themselves?
What would those worlds be like?
Well, without a star's warmth, they'd likely face an eternal freeze. But the fact that we see evidence for dust grains growing and clumping in brown dwarf disks, it points to the possibility. It's a fascinating, kind of spooky prospect.
Okay, this is all incredible background, but it really brings us to the ultimate prize, doesn't it? The Holy Grail, alien Earths, and the search for life.
Absolutely. The ultimate goal for so many.
And the Kepler mission really embodies that dream.
Oh, completely. Kepler was born out of Bill Baruch's just sheer, dogged determination over 25 years. He fought to get this mission launched.
Its goal.
Launched in 2009, its one clear goal was to find Earth-sized planets in Earth-like orbits around Sun-like stars, to figure out how common planets like ours actually are. It truly was, and its data still is, one of those exciting things happening in astronomy.
So when we talk about finding Earth-like planets, what does that actually mean? What are the Goldilocks conditions that make a world potentially habitable?
Right. The Goldilocks planet, not too hot, not too cold. Several factors are crucial. First, size matters. You don't want it to be too massive, say, more than 10 times Earth's mass, or tends to become a gas giant, sweeping up gas. But you also don't want it too puny, maybe less than a third of Earth's mass, because then it might struggle to hold on to an atmosphere, or it might lack geological activity like plate tectonics.
Plate tectonics, why is that important?
Plate tectonics seems to be really important for long-term climate stability. It helps regulate the planet's temperature over millions of years by cycling compounds like carbon dioxide between the atmosphere, oceans, and the planet's interior.
Okay, so size matters. What else?
The right orbit. Ideally, a fairly circular orbit so the planet gets even heating from its star, avoiding wild temperature swings between seasons or parts of the orbit.
Makes sense.
And of course, you need the right star and the right cosmic neighborhood. The parent star needs to be long-lived. Our sun will last about 10 billion years total, which gives life plenty of time. Even longer-lived red dwarf stars could be good candidates.
But you also need a safe neighborhood.
Yeah, you probably don't want to be too close to the chaotic galactic center, or in a really crowded star cluster where gravitational encounters or supernovae could be disruptive.
So all these factors together define the habitable zone.
Exactly. It's that region around a star where the temperature is just right for liquid water to potentially exist on a planet's surface, given enough atmospheric pressure. It's a delicate balance. Think about our own solar system. Earth is just right. Venus has a runaway greenhouse effect, making it hellishly hot. And Mars is too cold and lost most of its atmosphere, preventing surface water today.
What about planets around red dwarfs? You mentioned they're long-lived. They're also really common, right?
Incredibly common. Over 80% of all stars in the galaxy are red dwarfs. So their habitability is a huge question.
What are the pros and cons?
Well, incredibly long lives, trillions of years potentially, and planets in their habitable zones are much closer in, making them easier to detect via transits or radio velocity. Cons. Those close-in planets are likely tidally locked.
Meaning one side always faces the star.
Right. One side in perpetual daylight, the other in perpetual night. Plus, red dwarfs can be very active, unleashing powerful flares that could strip atmospheres or bathe planets in harmful radiation.
So are they habitable or not?
The jury's still out. Maybe thick atmospheres could distribute heat, maybe oceans could, maybe life could adapt, or maybe not. It's a really active area of research, and we shouldn't forget moons either.
Moons?
Yeah, you could have a rocky moon, like Earth-sized, orbiting a gas giant within the star's habitable zone. Think of Pandora from the movie Avatar. That's a scientifically plausible scenario.
Cool. Okay, we're also finding these super-Earths, right? Bigger than Earth, smaller than Neptune.
Yes, planets between roughly 1 and 10 times the mass of Earth. And Kepler data suggests they might be incredibly common, perhaps more common than Earth-sized planets.
Could they be more habitable than Earth?
That's a fascinating idea. Harvard's Dimitar Sasolov has argued yes, potentially. A bigger planet might have more vigorous geological activity, stronger magnetic fields, maybe retain its atmosphere better. Kind of a bigger is better argument for habitability.
But there's a counter-argument.
James Casting offers one. He suggests that while they might be habitable, it might take them longer to build up enough oxygen in their atmospheres to support complex life, if they ever do. So it may be better for microbes, but not necessarily for complex life as we know it.
And we might find really exotic types of Earths, too, like diamond planets.
That's a wild possibility. Researchers like Mark Kuchner and Sarah Seeger explored the idea of carbon planets. If a planetary system forms from a disk that's unusually rich in carbon instead of oxygen,
Uh-huh.
you could end up with planets made of carbides, graphite, and potentially, deep down under immense pressure, layers of pure diamond. There are hints of such carbon-rich disks, like around the star Beta Pictoris, worlds that would be utterly alien to our silicate rock experience.
So the search continues with ever more precise instruments.
Absolutely. Instruments like harps on the ground can detect incredibly subtle wobbles, pushing down towards finding true Earth-mass planets. There are dedicated searches targeting Alpha Centauri, our closest stellar neighbor, just 4 light years away.
Wow, that close.
And even smaller, focused ground-based projects like MIRF, which looks specifically at nearby red dwarfs, discovered GJ1214b, a mini-Neptune super-Earth, and we've even been able to study its atmosphere. Progress is happening on many fronts.
What was Kepler's ultimate potential haul? How many Earths did they expect?
Well, based on its initial survey, Kepler was expected to find hundreds of super-Earth candidates, and somewhere between, say, 50 and maybe over 600 Earth-sized candidates potentially within the habitable zones of their stars.
That's a lot of potential Earth.
It is. As NASA's Natalie Batalha, a key Kepler scientist, put it, we are all closet optimists. We expect Earths to be common. But, and this is a crucial but, finding an Earth-sized planet in the habitable zone doesn't automatically mean finding life. Just look next door at Venus. Same size as Earth. In roughly the right neighborhood early on, vastly different outcome. Habitable zone doesn't guarantee habitability, let alone life.
Right, so that's the next giant leap. If we find these potentially habitable alien Earths, how do we actually find definitive signs of life? This is where astrobiology comes in.
Exactly. Astrobiology is this amazing multidisciplinary field bringing together astronomers, biologists, chemists, geologists, all focused on this question. And we need to be realistic. The first detection probably won't be, little green men or winged humanoids.
No spaceships landing on the White House lawn.
Probably not. It'll likely be much more subtle. Probably an ambiguous spectral imprint, a hint in the light coming from an exoplanet's atmosphere that suggests something biological might be going on.
How do we even know what to look for?
A key insight came from Carl Sagan and his team back in 1990. They did this ingenious experiment. They used the Galileo spacecraft, which was flying past Earth on its way to Jupiter, to look back at our own planet as if it were an unknown exoplanet.
Turning homeward, yeah. What did they find?
They found several things, but the most telling was evidence of an atmosphere in severe chemical disequilibrium. Meaning it contained gases that shouldn't naturally coexist in large amounts because they react with each other. Specifically, abundant oxygen, O2, and methane, CH4.
Why shouldn't they coexist?
Because oxygen rapidly destroys methane. To have both present in large quantities implies something is continuously producing both gases, and on Earth, that something is life photosynthesis producing oxygen and microbial life producing methane. As Sagan's team concluded, finding such disequilibrium is a strong pointer, and life is the hypothesis of last resort to explain it.
So we look for atmospheric combinations that seem unnatural without biology?
That's a major strategy, yes. And we can use Earth itself as our benchmark. Studies of Earthshine sunlight reflecting off Earth onto the dark side of the moon, which we can then analyze.
Clever.
They show us what Earth's spectrum looks like from afar. We see clear signs of water vapor, oxygen, ozone, O3, which is formed from O2, and even something called the red edge signature.
What's that?
It's caused by chlorophyll in plants. Plants strongly reflect near-infrared light, creating a sharp increase, an edge, in the spectrum at red wavelengths. It's a potential sign of widespread surface vegetation. Nicholas Cowan even used data from the Deep Impact spacecraft looking at Earth to show how variations in brightness and color over time could let us infer the presence of continents, oceans, and clouds on a distant world.
So what are the most reliable biosignatures we're looking for?
Well, oxygen and its byproduct ozone are considered pretty strong candidates since photosynthesis, as we know, it produces so much oxygen. But we have to be cautious because there might be non-biological ways to produce oxygen or ozone in certain planetary atmospheres, maybe involving intense UV light splitting water vapor. So finding oxygen alone might not be definitive proof.
What would make it more convincing?
Finding oxygen along with a reducing gas like methane. As we said, they shouldn't coexist without a constant source, likely biological. Detecting multiple biosignatures simultaneously, say O2 or O3, plus water vapor, plus maybe methane or nitrous oxide, that would build a much stronger, more convincing case that we found something truly extraordinary. Life.
Are people exploring other, maybe weirder biosignatures too?
Absolutely. There are projects like the Virtual Planetary Laboratory, or VPL, that use computer models to simulate all sorts of weird and wonderful planetary environments, different star types, different atmospheric compositions,
Hmm.
and they try to predict what unique biosignatures might arise in those alien conditions. Maybe life on a red dwarf planet uses different pigments for photosynthesis, creating a blue edge in the spectrum instead of red one, or maybe even black plants absorbing almost all light. The possibilities beyond Earth-like life are vast.
So when might we actually detect these? What's the timeline?
Well, definitively detecting biosignatures like oxygen and methane together in an Earth-like planet's atmosphere, that's likely going to require future dedicated space missions. Things like NASA's proposed Habitable Worlds Observatory, or maybe concepts similar to Europe's earlier Darwin proposal.
Right.
These are big, ambitious telescopes designed specifically for that task.
But what about nearer term? James Webb.
The James Webb Space Telescope, JADE in UST, offers some exciting prospects. It's incredibly powerful, especially in the infrared. While finding oxygen on an Earth twin might be tough for Webb, it can study the atmospheres of some transiting planets, especially larger ones like super-Earths or mini-Neptunes, perhaps orbiting red dwarfs. It might detect water, methane, carbon dioxide, potentially giving us our first real atmospheric clues for potentially habitable worlds. So the future is definitely near in terms of making progress.
And we can't forget SETI, right? Listening for signals.
Absolutely not. SETI, the search for extraterrestrial intelligence, is a complementary approach. From Frank Drake's pioneering Project Ozma back in the 60s to modern efforts using large facilities like the Allen Telescope Array. Listening for deliberate artificial signals is a different way to ask the question, are we alone? It's a high risk perhaps, but the potential reward is obviously immense.
Finding any life, though, even just microbes, that would be huge, wouldn't it?
Oh, finding definitive evidence of life beyond Earth, even primitive microbial life, would be a scientific and philosophical revolution on par with Copernicus realizing Earth wasn't the center, or Darwin explaining evolution. It would fundamentally shift our understanding of our place in the universe.
Given everything we've talked about, the sheer number of planets, the ingredients for life seeming common.
Right, the evidence for the apparent ubiquity of planets and the cosmic abundance of life's ingredients,
Mhm.
water, organic molecules, it does make it seem, well, maybe absurd, if not arrogant, to assume we're the only technological civilization or even the only life in the entire galaxy.
But assuming is one thing, proving it is another.
Precisely. The search for that proof, that definitive evidence, that's the ongoing quest.
And that takes us pretty much to the end of our deep dive today. What a journey. We've gone from ancient philosophers wondering about other skies, through Galileo's telescope, into the cosmic kitchens where planets get cooked up, to the incredible ingenious ways we're hunting for these alien Earths, and now the meticulous search for actual signs of life.
It's an amazing story, still unfolding.
It really feels like this exploration is far from over. You said we're in the Bronze Age.
I think so. The golden age is still ahead of us, definitely.
Yeah.
The capabilities we're developing now, the telescopes coming online like Webb and future missions, they're going to continue to surprise us, probably with discoveries we can't even imagine yet.
Okay, so the final thought I want to leave everyone mulling over is this. That dramatic moment, the first definitive evidence of life elsewhere, whether it's microbes or maybe even something more, it may well occur in our lifetime, if not during the next decade.
It's a very real possibility.
So the question for you listening is, what will you do when that news breaks? How will it change how you see the universe and maybe how you see our own small, precious blue planet? Something to think about.